Good morning. My name is Anusri Anil, final year MSc Physics student from Regional Institute of Education, NCRT, Mysore. And today, in this video, we are going to discuss about properties of nanoparticles in comparison with bulk. Nanoparticles often have different chemical and physical properties when compared with the same materials in large scale. As material gets smaller, when they are transformed from bulk form to nanoparticle, their properties alter. Materials at nanoscale are frequently reported to have unique optical, electronic, or mechanical properties. It is these properties that have made nanoparticles an increasingly popular field of study. Researchers are committed in understanding how the nanoscale versions of materials behave and what properties they have to exploit them and establish new and useful applications with new capabilities. So, what are nanoparticles? Nanoparticles are particles of matter that are between 1 and 100 nanometers in diameter. They exhibit various unique properties compared to their bulk counterparts due to their smaller size. We are going to discuss about the properties of nanoparticles with examples in this video. The first property which we are going to discuss is surface area. Nanoparticles usually contain just a few hundred atoms and they have very high surface area to volume ratio. The picture here shows us how the surface area is getting increased when the bulk material is converted into nanoparticle. This increased surface area enhances their reactivity and interaction with surrounding environments. Specific surface area is a material property that has particular importance in case of adsorption, heterogeneous catalysis, and reaction on surfaces. It is also found that materials which are inert in their bulk form are reactive when produced in their nanoscale form. For example, commercial grade zinc oxide has a surface area range of 2.5 to 12 meter square per gram, while nanoparticle zinc oxide can have surface areas as high as 54 meter square per gram. The nanoparticles of zinc oxide have superior UV blocking properties when compared to the bulk material, making them useful in applications such as sunscreen. The next example which we are going to discuss is mesoporous silica. Mesoporous silica nanoparticle is used as host materials for transporting therapeutics medicaments or encapsulation of molecules due to their capability to attach target ligands for specific cellular recognition or the design of well-defined tunable porosity. The image shown are SEM image of mesoporous silica. A, B, and C are images of prepared mesoporous silica nanoparticles with their mean outer diameter. First one, that is A image, has 20 nanometer diameter and B have 45 nanometer and C has 80 nanometer. The next property which we are going to discuss is optical properties of nanoparticles. Nanomaterials exhibit a variety of unusual and interesting optical properties that can differ significantly from the properties exhibited by the same bulk material. An optical response in a nanomaterial can be created through several different mechanisms depending on the nanomaterial size, composition, and arrangement, and each method may provide certain benefits depending on the target application. The figure here shown are different solutions of gold nanoparticles and gold in bulk. We can see the color difference in 3. This is because of the change in band gap. The distance between band gap changes with the size of the particles. Thus, the wavelength emitted during the transition between these energy levels will be of different colors. Nanoparticles made of semiconductor materials often referred to as quantum dots or QD, absorb and emit light at certain wavelengths that depend strongly on particle size and shape. By changing the size and composition of quantum dots, their emission wavelengths can be tuned from the UV through the visible to the near infrared region of the spectrum. For example, by tuning the size of cadmium selenide quantum dots from 2 nanometer to 8 nanometer in diameter, the emission wavelength can be shifted across the visible spectrum with a smaller particle emitting in the blue and the larger particle emitting in red. The figure here shows cadmium selenide quantum dots. And this is what I have discussed previously. The change in band gap distance is giving out wavelength of different colors and thereby we see different colors. Now let us discuss the third property, that is mechanical property. Nanoparticles may exhibit different mechanical properties compared to bulk materials due to their size effects, such as increased strength and ductility or decreased hardness. Mechanical properties like physical properties such as strength, melting point, etc. shows drastic change in nanoscale level. As nanoparticles are added to a common material, these particles will refine the grain to a certain extent, forming an intragranular structure or an intergranular structure, thereby improving the grain boundary and promoting the mechanical properties of material. The picture here shows how the elastic modulus E and hardness changes with respect to the diameter, or how it varies as the size of the particle increases or decreases. And clearly we can conclude from this graph that smaller is stronger and stiffer. Now let us discuss about melting point. The melting point goes on decreasing with decrease in size. The picture here shows gold nanoparticles of various size. The graph shows how melting point decreases with a decrease in gold nanoparticle. It is a melting point depression diagram of gold nanoparticles. Melting point can be simply defined as the temperature at which solid turns to liquid. According to microscopic definition of a substance, it is defined as the temperature at which molecule in it possess just enough energy to overcome intermolecular forces that hold them in a fixed position in a solid. Atoms on the surface of a substance requires less energy to move because they are in contact with lesser number of atoms of the substance. While atoms inside the bulk of sample are surrounded by large number of atoms and require more energy to move. At nanoscale level, if size of object is changed, then percentage change in number of atoms on the surface is very large. Due to this, melting point starts depending on the size of object and melting point goes on decreasing with decrease in size. Let us see some examples. Compared with microscale monolithic alumina ceramics, nano aluminum oxide ceramics have higher flexural strength. The image here shows nanoforms of alumina. It shows microstructure of monolithic alumina, ytterstabilized zirconia, and conventional alumina-zirconia composite. Second example is nano silicon oxide. Adding 3 weight percentage of nano silicon oxide to concrete can improve its compressive strength, bending strength, and splitting tensile strength. The image here shows silicon powder as viewed by naked eye and SEM image of the same silicon oxide. Now let us move on to the third property, that is chemical reactivity. The high surface area and surface reactivity of nanoparticles make them highly active in chemical reactions, particularly in catalysis, where they can enhance reaction rates and selectivity. Nanoparticles exist far from the equilibrium state due to their high surface energy. The atoms in nanoparticles have a higher average energy than atoms in longer structures because of their larger proportion of surface atoms. For example, catalytic materials have a greater chemical activity per atom of exposed surface as the catalyst is reduced to nanoscale. Now, let us take an example and compare the properties in bulk form and in nanoparticle form. Let us consider platinum for the time being. In bulk platinum, the catalytic sites are primarily located on the surface of the platinum foil. While bulk platinum can catalyze the carbon monoxide oxidation reaction, its limited surface area results in fewer active sites available for adsorption and reaction. Consequently, the reaction rate may relatively be slower compared to the nanoparticles. Platinum nanoparticles, on the other hand, offer a significantly larger surface area due to their small size and high surface to volume ratio. This increased surface area provides a greater number of active sites for carbon monoxide adsorption and subsequent reaction with oxygen molecule. As a result, the catalytic activity of platinum nanoparticles in carbon monoxide oxidation is substantially higher than that of bulk platinum. The figure shows platinum nanoparticles solution. Moving on to the next property, the property which we are going to discuss is magnetic properties. Magnetic nanoparticles exhibit superparamagnetism, that is, retaining their magnetization even after when the external field is removed. This property makes magnetic nanoparticles highly useful in various applications such as magnetic storage, biomedical imaging, and targeted drug delivery. Nanoparticles are more magnetic than bulk materials. Even non-magnetic solid materials becomes magnetic when reduced to nanoscale. For example, bulk gold and platinum are non-magnetic, but at nano size they turn to magnetic. The magnetic nanoparticles are mainly made from magnetic materials such as iron, cobalt, and nickel. The magnetic properties, including the saturation magnetization, remnant magnetization, and coercivity of iron oxide, or commonly known as black iron, that is Fe3O4 nanoparticles, are highly influenced by the particle size and domain structure. The saturation magnetization increases with increasing particle size, regardless of the crystal structure and particle shape. The picture shown here is the highly crystalline Fe3O4, that is iron oxide, and the graph shows the correlation between particle size or domain structure of highly crystalline Fe3O4 and their magnetic property. Now let us move on to the next property, that is electrical properties. The properties like conductivity or resistivity comes under the category of electrical properties. These properties are observed to change at nanoscale level just like how optical properties change. The examples of the change in electrical properties in nanomaterials are: as the size of gold nanoparticle decreases, quantum confinement becomes more and more pronounced, leading to changes in electronic band structure and potentially altering the electrical conductivity. In simple words, we can say that as the nanoparticle size decreases, the gap between or the distance between the conduction band and valence band increases. That is, the energy gap distance increases, which alters the electrical property of the material. Surface ligands, defects, and interactions with surrounding environment can also affect the electrical properties of gold nanoparticles. Now, let us discuss some more examples wherein the electrical properties are altered in bulk form and in nanoparticle form. Bulk graphite exhibits good electrical conductivity due to the delocalization of electrons within its layered structure. Carbon nanotubes, depending on their chirality, can exhibit metallic or semiconducting behavior with exceptional electrical properties surpassing those of bulk graphite and other conventional materials. The figure here shows what I have discussed earlier, that is, as the particle size decreases, the distance between conduction and the valence band increases, that is, the energy band gap increases, which will change the electrical properties of any material. Next example is silver nanoparticle. Silver nanoparticle have proved to exhibit excellent electrical conductivity. The figure here shows SEM images of silver nanoparticles. Now we are going to discuss about the next property, that is thermal conductivity. So what is thermal conductivity? Thermal conductivity is a measure of a material's ability to conduct heat. In bulk materials, heat is typically transferred through lattice vibrations known as phonons. However, at nanoscale, the behavior of phonons can be significantly altered due to quantum confinement effects, leading to changes in thermal conductivity. The size-dependent thermal conductivity of nanoparticles allows for the engineering of materials with tailored thermal properties. By controlling the size, shape, and surface characteristics of nanoparticles, researchers can design materials with desired thermal conductivities for specific applications ranging from thermal insulation to thermoelectric energy conversion. Now, let us see the example for studying the thermal properties of nanoparticles. Silicon nanoparticle. In bulk silicon, heat is efficiently conducted through the crystal lattice with minimal scattering of phonons. However, when silicon is in nanoparticle form, typically ranging from a few to several tens of nanometer in diameter, the increased surface area results in high density of surfaces and interfaces where phonons can scatter. That means it can conduct heat in a more efficient way when it is in nanoparticle form. The figure here shows different porous form of silica. Now I am going to talk about the last property which will be discussed in this video, that is quantum effect. At the nanoscale, quantum mechanical effects become significant, influencing the electronic, optical, and magnetic properties of nanoparticles. These effects arise due to the confinement of electrons and the quantization of energy levels, leading to phenomena such as quantum confinement, tunneling, and discrete energy states. As the size of quantum dots decreases, the energy levels of electrons and holes become quantized, leading to discrete energy states. This quantization results in size-dependent optical and electronic properties such as a tunable bandgap and discrete energy levels. So, what is quantum confinement? Quantum confinement refers to the phenomena where the motion of charge carriers such as electrons and holes within a material becomes restricted in all three dimensions due to the small size of material, typically on a nanoscale. The picture here is the depiction of quantum confinement effect which arises from the discretization of electronic energy states. In summary, quantum confinement effects in nanoparticles exemplified by semiconductor quantum dots enable precise control over their optical properties, making them valuable building blocks for advanced nanophotonic and optoelectronic devices. The discrete energy levels in quantum dots give rise to another quantum effect known as tunneling. Quantum tunneling is a phenomenon in which particles penetrate a potential energy barrier with a height greater than that of total energy of the particles. This phenomenon is of great importance because it violates the principle of classical mechanics. One of the most significant applications of the tunneling effect of nanoparticle is in scanning tunneling microscopy, that is STM, which is used to create images of surface at atomic level. In conclusion, The properties of nanoparticles are of paramount importance due to their versatility and unique characteristics, offering tailored functionality and enhanced performance across various fields. These nanoscale materials enable advancement in medicine, electronics, energy, environmental remediation, and beyond, facilitating innovations in targeted drug delivery, diagnostic imaging, miniaturized device, and pollution mitigation strategies. Thank you for watching this video.